All right, welcome everyone. Today we are having a PacTrans Doctoral Webinar Series presentation by Zhiyong Cui. And I'll get a little bit more into who he is and what he will be presenting on. But I just want to start by introducing this platform, what it is, and kind of why it's important. So this platform we've developed to provide a space where PhD students can share their work to other people who are interested in the subject in sort of a way that's not really available in other places, because you can do presentations at conferences or in other areas, but oftentimes those places don't provide a way for deep discussions to form to discuss these topics, because oftentimes PhD students are doing the work that is the most cutting edge in whatever field they may be, in working with whatever PI or other advisor they may have. So we formed this platform as a way to create sort of an intimate discussion environment to talk about some of the most cutting edge and critical research that's going on in the transportation field today. So today we have invited Zhiyong Cui to come speak with us. And he is a PhD student from the University of Washington. And typically, I'll say the introduction of the student is usually done by their advisor. However, unfortunately, his advisor, Dr. Yinhai Wang, has a time conflict, so I will be introducing him. He is a lab mate of mine, so I feel like I'm at least somewhat qualified to do so. So right now, Dr. Zhiyong Cui is a postdoc in the civil engineering department at the University of Washington, where he also earned his PhD degree in 2021. He has a master's degree in software engineering from Peking University and a bachelor's degree in software engineering from Beihang University. Those are in 2015 and 2012. So Dr. Cui's current research includes intelligent transportation systems, transportation data science, short-term traffic forecasting, and smart vehicle infrastructure and control. He also serves as a member of the TRB Standing Committee on Intelligent Transportation Systems and a member of the ASCE Transportation and Development Institute Artificial Intelligence Committee. Without further ado, I will turn it over to Zhiyong and he can present on the topic today.
Yeah, okay. Thanks for the introduction from Sam, and maybe I can start this talk. So hello, everyone. I'm very glad to have this opportunity to present in this PacTrans Doctoral Webinar series. And also, so today my talk is about deep learning for short-term network-wide road traffic forecasting. And this is basically the presentation. This is the topic of my doctoral dissertation. And so today, in today's presentation, I will mostly introduce some of my PhD research work. And then I would also briefly talk about the new trend in this research area. So let's start. So you may wonder, like, mostly, like, if you find this topic, you can understand what is that. But if you are not very familiar with what is short-term traffic prediction, then I can just give you a very simple example. Normally, we see that traffic prediction is like we try to use some historical traffic data to predict the traffic state in the future, right? And the short term means we just want to predict the traffic state, such as speed or volume, in a very short term time period, maybe just 1 hour, half an hour, or maybe 10 minutes. It can also vary from maybe several minutes to several hours. So different research will have this kind of temporal scales. But like in this figure, you can just see that one figure shows the ground truth traffic speed, and the other one shows the prediction of those kind of traffic speed. So that's basically how we did with like traffic prediction for one location. Well, sometimes we may need to do traffic prediction for even a corridor or like a freeway like this. We need to predict the traffic states of all those kind of locations here. And that's not a very hard problem, because this traffic prediction or traffic forecasting study has been, there's a lot of work has been done in this area. But like in the recent several years, one hot research topic is network traffic forecasting. It become hot not because of this is a more complicated research area. It's also because we have some new tools such as machine learning tools, deep learning tools, and they have a lot of they have kind of like more power to dealing with this complex data. And I think in the near future, we may need to also consider we want to predict the traffic stage of all the roads, even in the link level, like even in the lane level, like the figure shows here, right? And then as we can see that right now we have a lot of new sensors. For example, we have some cameras and other type of sensors. We have our phone, and in the near future, we may have the Internet of Things. Like we can have several edge devices. So in that case, we have a lot of data we can use for those kind of prediction tasks. And plus with AI, like the new technologies, even not only AI, like some other communication technologies, this traffic prediction can actually have a lot of important applications. The first one can be autonomous driving. You need to know the traffic states on the roadway, especially in front of the vehicle, right? And it can also help to manage the traffic. If we know the future traffic, then we can manage how to control the traffic signal or control some traffic metering devices. And it is also very important for predict or see to route to plan your trip, given origin and one destination. You can easily find the shortest path on Google Drive, right? So this is also related to traffic prediction. And the next thing is this figure. I just want to show you that you can see deep learning based traffic prediction, or say traffic forecasting, is a new research area. And this figure just shows the number of applications in the past several years with the topic of deep learning based traffic prediction. And so this is basically a collection of topic with the terms can be deep learning or deep neural network, traffic forecasting, or traffic prediction. And definitely it does not include all the publications in this area, but you can see the trend. And so the figure shows this research area is pretty popular, but like, what is the reason? As I mentioned, it is not because of the new data set. It's also because of we have plenty of new tools or more powerful tools. That's the deep learning. And one example, like why we need to develop deep learning based traffic, is that you can see in the right figure. In 2020, actually, DeepMind collaborated with Google Maps. They developed some like real-time ETA prediction. ETA is the estimation of the estimation time of the arrival. So you can see they just use some very novel and advanced deep learning methods, such as graph neural network, and the estimated ETA was improved up to 50% in the city all over the world. And so that's a very important and useful application for us. So that's why we want to implement the deep learning, especially in the traffic prediction area. So that's the background. And in this presentation, actually, it mostly comes from my dissertation. And in my dissertation, I have actually split the research into 3 parts. The first part is kind of like we'll try to design some deep learning methods to learn the spatial and temporal feature from the traffic data and to conduct traffic prediction. And in the second part, I just want to deal with one issue in traffic prediction, which is the missing value. Like we sometimes encounter that the spatial temporal data has some missing values. We just try to deal with these missing values during the traffic prediction. And the third part is actually try to deal with transportation data and try to build some applications. And so in today's presentation, I will mostly focus on the first part and second part. And as I listed here, the first part is the first and the second part are mostly trying to design some algorithm to solve the traffic prediction task. Well, you can see that this type of work can be categorized into two groups. Well, the first one is we learn the traffic traffic data as a matrix, and the second part we learn the traffic data as using their topology properties and learn the traffic roadway network as a graph. So that's the two parts. So maybe you can first come to the part 1 right now. Here, I'll just quickly give you another example of what is the traffic prediction, especially what is the network-wide traffic forecasting. So here, we may have some historical network-wide data you can consider. That's the roadway network in the Seattle area. And so the traffic state is represented by the color on the roadway network, right? And what we want to do is, given these historical traffic data from time 1 to time t, we want to estimate the traffic state in time t plus 1. And this is only one time, one step prediction. You can also conduct a multi-step prediction, but in my research, we just mostly focus on single step prediction here. And the traffic states actually can be represented by some vectors or some symbols. You can consider we use X to represent the traffic state of the whole network. And so this kind of X can actually, in each time step, it could be a vector. Since we have S links in this traffic network, then this X would be a vector with a dimension of S. So here, this figure shows you a more intuitive way, what is the traffic prediction here. So our task will be learn a function f. Is no matter what is the methods or formulation of the f function, we just need to take the vector from x1 to xt as the input, and we will generate xt plus 1 vector as the prediction result. So here, if we want to learn the traffic as a matrix, sometimes we need to deal with those kind of vectors. We combine them together, right? One dimension is the temporal information, and the other one is the spatial dimension. So we deal with this traffic data as a matrix. Sometimes it looks like this. And what we want to do is we try to predict the future traffic states, it could be like this. So this is just a very simple example. And then the major component of like traffic prediction is mostly the temporal information study or temporal dependency learning. So it means that we need to capture the temporal relationship between the data, or it can be a correlation. So this kind of work, especially single location-based traffic prediction, has been studied for a long time. A lot of classical methods, such as autoregression, has been used, or some even complicated methods called ARIMA. But like in the deep learning field, or in the deep neural network field, a lot of new methodologies has been applied, such as recurrent neural network and its variants, including the long short-term memory and also the gated recurrent. So if you are not very familiar with this kind of recurrent neural network structure, it looks like this. So as I mentioned before, right, we have the input. We can consider those X as the input, and so given one step, it will be inputted into this recurrent neural network cell. It will generate an output, and then this information will be moved to the next step. Then the new time step input will be accepted by this cell, given the information. So it will generate another output. So you can consider this RNN is like it recurrently accepted the input and generated the output. So it is quite useful to deal with some sequential data here. And this LSTM is kind of a more complicated structure, but the logic is the same. And this LSTM cell, it can be just like the RN cell like this. So you just have some more complicated input and output. So you can refer to some literature to check the details. So another thing is that sometimes we want to deal with data, especially the temporal data. Sometimes we use a bidirectional RN. That means when we have two LSTM, and this data can be inputted into these two cells. But the order of processing the data is in two ways. One is the forward direction, the other is backward direction. That means we can easily deal with the temporal information in two directions. That may give us more comprehensive understanding of the pattern of the, especially the temporal pattern of the data. So here, like sometimes you may wonder why we need a bidirectional, because the forward and the backward temporal dependency is kind of sometimes if you have the historical data, you can actually get the forward and backward temporal dependency. And our traffic data, normally it has some periodicity, right? So in this case, you can use the bidirectional LSTM or RN to better capture the pattern in the data. So this is one work we have done. So we proposed one framework. This very simple. You can consider it has a one input layer, and it's followed by a bidirectional LSTM layer. And after that, you can actually append more bidirectional LSTM layer here. And in the last layer, we just put one LSTM to fulfill the prediction task. So that's one of the research we have done. And based on our comparison with some other structures, we found that this structure is better than the pure LSTM and bidirectional LSTM. This is just because we have sometimes the performance is better just because of we use more layers, and sometimes it is because the structure is good. So this is only the earliest work we have done, but in this case, we show that at least the bidirectional LSTM is more powerful, especially when we deal with the temporal data. Well, in the next slides, you can see that's the ground truths and also the predicted information. The left one shows, especially in those figures, the horizontal axis shows the spatial information, and the vertical axis shows the time of day. So you can consider that's a heat map during one day, and so their axes are the same, and so you can consider their patterns is almost the same, right? But that also shows the prediction accuracy of those kind of work. And as I mentioned, this is only just one early work, and we just try to use bidirectional RNN to deal with the temporal pattern. Well, how normally do we have some even more powerful way to deal with the spatial information in the traffic? Because you can see in this study, we just concatenate the spatial information in some specific order, but it does not follow our understanding of what is the spatial arrangement of those roadway networks, right? So in this way, I just want to mention another very popular research area. It is the graph neural network. And so in this study, we just try to learn the traffic network as a graph. And you may wonder why we want to learn the traffic network as a graph. The main reason is that sometimes when we deal with the traffic network, it is a very complicated roadway network like this. And so basically, if we learn the traffic data like this, if you learn, if your input data is an image, you may use the convolutional network, but there's a lot of blank areas, right? It is quite inefficient to do that. So sometimes we convert each roadway link as a node, and their intersection will be the link between the nodes. So in this way, we can convert those kind of traffic network as a topological graph like this. So in this case, the traffic prediction task can be a little bit complicated. So given a graph, normally we will have their vertices and their edge. We also need to understand what is the adjacency matrix, and this adjacency matrix just measures what the connectedness between the nodes. So the traffic prediction task will be a little bit different. In this case, we will take the graph as the input. So here you can see this is a very simple example of what is the adjacency matrix. It only shows the connectedness between different nodes. So if two nodes are connected, then the element in the matrix will be 1. Otherwise, it is 0. And sometimes we also deal with adjacency matrix a little bit because we want to add the identity matrix here to ensure that the nodes are self-connected. That means the elements in the diagonal area will be 1. So here we just show you an example. What is the adjacency matrix here? Like if take the red star as an example, we take the first order, like the one hop adjacency matrix. It just measures which node is connected to the right one. And if we take the 2 order, then that means all the highlighted nodes have 2 hop of connectedness with respect to this this right star here, right? So just illustrate what is the meaning of adjacency matrix here. And when we deal with a graph neural network, a very normal way, or say a popular way, is to conduct the graph convolution. Well, this graph convolution, sometimes you can just sum of all neighbors factor feature factor. Sometimes you can also use some different ways, especially using spectral ways to conduct the graph convolution. And there's a lot of different definitions you can check. So the meaning of convolution is that we just try to, we have a sliding window like this. So we just try to get the convolved feature in this local area, and then we can move this sliding window to get more feature in the whole matrix. And the graph convolution is kind of in a similar way. We just try to get some local features from this for this graph structure, right? So that's the graph convolution. And in our studying, so because the roadway network is consisted of the roadway segments, and those roadway segments are different actually. So we take the underlying physics of the roadway network into consideration. Especially we consider that the traffic impact will be propagated to its adjacent segment, right? And this impact of transmission between those non-adjacent nodes cannot be bypassed by the intermediate nodes. So that means if a traffic can be propagated to some nodes, that means these two nodes must be connected, and we just try to measure whether those traffic impact can be reachable between two nodes. So we define a free flow reachable matrix here. That's the definition, and the a more intuitive way to understanding what is the free flow reachable matrix is that we still take the right star as an example. So given a time period, if a vehicle is on the right star link, then it will travel with the free flow speed, right? So this green part shows how far a vehicle can arrive during a specific time period under the free flow speed. Then if the node is covered by the green link, then that means this node is free flow reachable to this red star. So that's the definition. And based on that, we propose a traffic graph convolution. And so you can consider we just try to measure the localized feature in the graph. And so that's the graph convolution operation we made. It is pretty simple. Like you can consider we just multiply weight matrix with adjacency matrix and another free flow reachability matrix as we defined. And this operation is the element wise matrix multiplication operator. So given input x, like it can be a vector here, it will firstly multiply with a weight matrix, which is a square matrix, and then it will multiply with actually using the element-wise matrix multiplication with these two matrices, and then we can get the graph convolution here. So that's basically the traffic graph convolution we take different hop or say different order of the traffic graph convolution. And then, so that's the framework. We just try to first select some spatial feature before those input data is inputted into the LSTM. So that's a very a common structure in these days, but this work has been done maybe 3 years ago. So at that time, it is kind of novel, but right now, a lot of work has similar structures. As you can see, that's the basic overall structure. This is like the cell of the recurrent neural network. And this slide only shows you the difference between the LSTM and also the proposed TGC-LSTM. It is pretty similar. We just try to replace the input with the feature we learned. And then we also conduct some graphical constraint on the formulation here. So in this case, we conduct several experimental studies on different data sets. One is the freeway data set in the Seattle area, and the other one is the like arterial in the downtown Seattle area. And we found that actually in our model outperformed some standard of art method. It also outperformed some baselines, especially some like very basic classical machine learning methods. And then this figure shows the results, especially this one shows the speed of the converge using showing the validation loss of different methods. And the right part shows the training time. And so our work actually, it takes some more time. It take more time than the normal LSTM, but like the training time actually is acceptable because they are on the same level actually. And then the next slides will show you the advantage of this method. So as you remember, we have a weight matrix, right? In the definition, this weight matrix is used to estimate the connectedness or see the relationship or see the dependency between different row segments. And we highlighted actually we visualized this graph convolution weights, and we highlighted some area with darker color. And so those color actually, or say those highlighted regions located in some key area in the roadway network. For example, like this area, like the most dark green area, actually that's one like ramp area on the SR 520 corridor. So that means these kind of graph convolutional weights can be somehow interpreted by visualizing the data onto the real map. So in this case, this method is actually like kind of interpretable. So that's one contribution of the methodology we proposed. And also we also deal with some like deal with the data using different methods, such as this gated graph wavelet recurrent neural network. Due to the time limitation, so I will not present it today here, but you can refer to the paper. Then the next part is the traffic prediction with missing values. So this part is kind of a little bit different. So let me introduce the problem again. So this is the traffic prediction, right? As we saw before. The problem is sometimes our data have some missing values due to the device failure or due to some collection methods problem. So as you can see, you can consider those black area are the missing values. Then a very intuitive understanding of this problem is that this missing value will affect actually the prediction accuracy, right? So sometimes if we deal with the missing value on just one segment, it is pretty simple. We can just do the interpolation, right? And then if we want to deal with the network-wide missing value, we can still deal with that. We can first conduct the interpolation and then fulfill the traffic prediction in the next step. So that's the normal way we deal with the problem. That's two-step. We first fill the missing value and then we predict the future value. There's a lot of ways we can deal with the missing value, such as PCA or matrix decomposition sometimes. But actually, in our study, we try to deal with this problem using just a one-step method. So we want to solve the missing value issue and the traffic forecasting issue at the same time. So in this case, the define of the problem will be even more complex. So we will use a mask vector to demonstrating where is the missing value. So the masking vector look like this. We use M here. If one cell is missing, then the indicating area will be 0. Otherwise, it is 1. So in this case, we will have the input X, the masking vector, and also the graph information as the input. We just want to learn this F function to conduct the traffic prediction. So previously we have used some LSTM structure-based method. We just add one imputation unit to fulfill this task. The challenge is that we cannot learn the localized features, and also it lack of some interpretability. So inspired by the graph convolution we mentioned before, so we propose another method. It is the we actually incorporate two properties of the traffic information into consideration. The first one is the Markov property. So that means if we have a traffic state, then the traffic state xt plus 1 is mostly determined by the traffic state at time t, and this xt it actually depends on the previous time step, like the xt plus 1. So that's the Markov property we proposed, and so we can represent this property using a formulation like this. So we just use a transition matrix to multiply with the input x. Then we can get the traffic state of the next step, and we also add actually multiplying a decay parameter gamma here. So that's the Markov property. And then we also consider the graph localization property. This is very similar to the graph convolution as we mentioned. So we just try to estimate which node is connected with a specific node here. So by multiplying the adjacency matrix with the input vector, then we can get the output, which can kind of summarizing the local feature and then get an output like the xt plus 1 here. So here we just want to combine these two properties together, and we combine these two equations together like this. So in this case, it defines a graph Markov process. So that means, so what is the exact means? This figure shows the logic here. So if we want to predict the traffic state at a time t plus 1, and especially we want to predict the cell in this area. So basically, this node is connected with 4 nodes, right? As you can see, we can just use the value of these 4 nodes to infer the value of this right node. But however, there's one node, like the value is missing. Then how can we deal with that? So we just use the same logic. We firstly try to find which nodes are connected with this gray one, and then we just try to get the information from the previous time step. And if there's still some missing values, we can iteratively use the same logic to infer the traffic information on those nodes. So in the end, all the nodes, or say the value of the vector can be inferred from the previous ones. So that's the basic logic. And then here, as you can see, we just try to handle the missing value in the graph Markov process. We define a completed state. It combined with the actual value and the inferred value. So the transition of the completed state follows the graph Markov process. Basically, this equation shows that we have the transition of the completed state. Well, this H is demonstrating this multiplication. So we just use H for simplicity, and so we can iteratively apply the X tilde, like the completed state, into this equation. So you can see this is a new one, and when we apply this blue area by itself, then we can get a new equation. So in the end, we can represent the transition process using an equation like this. And these are the multiplication and summation area, and we have another term here. And this term actually can be neglected if the timestamp is long enough. So that's the graph Markov process, and we also have a graph Markov network. So this is the graph Markov network. Actually, it's defined based on this Markov graph Markov process. You can see they have the similar equation definition, and we have two versions. The other one is a spectral graph Markov network, and so they are kind of similar. Only the graph convolution operation is different. So that's the basic neural network structure here, and we conduct the experiments on 3 different data sets. One is the data set from Bay Area, the other one from LA, and the third one from Seattle. So we compare our model with different baseline methods, look like showing here. So in this case, that's the predicted result on different data sets. That's the performance on Bay Area data set. This one is the performance on the LA data set, and that's the Seattle data set. The proposed method actually it can reach at least at the same level of the baseline methods shown here. As you can see, the spectral ones perform even better than the normal ones. So yeah, so that's the basic result. And for the other property of the proposed method, so because we think about the model, it only have some multiplication and summation. So the structure is pretty simple. That means the training time is pretty is much less than the other methods. And the model has also some good properties, especially the interpretability. Based on the graph convolution, based on the graph weight matrix, we can show some top some nodes with the most influence on its neighbors. So we illustrate that those nodes on the LA map. And so this figure shows the spectral version. So for the orange node, you can see its effect on its neighbors. So we use different color to show the level of the effect. So that's the model interpretability. And then the next part is actually the forecasting result. We show you the ground truths and also the prediction result of different methods on the 3 data sets. And you can see that's basically the prediction performance. So basically that's the second part I want to introduce. And it basically, we try to develop some methods to deal with the missing value. And based on that, we actually developed some applications such as this traffic.ai is a AI-based platform. We also develop TPS, like traffic performance score website. So we implement some traffic prediction functions on this platform. And actually in my dissertation, I also introduced some data integration methods, but I will not introduce in today's presentation. And then, so I just want to quickly illustrate the transportation AI platform. It can actually show you some traffic prediction data set And we also show the prediction results. So you can find some source code in this website. And the other one is the TPS. So actually this one is, we just try to monitor the traffic performance in the Seattle area, but we implemented one prediction function on that. So that's basically based on the work we have done. So this is the third part. I will just skip. So in summary, in my dissertation, actually, we have 3 parts, but you can consider the first 2 parts are the theoretical or algorithmic contributions. And the other part is some application contributions. And today, I just want to give you a brief understanding of what is the deep learning based short-term traffic forecasting. Well, actually, in this research area, a lot of paper emerge in recent years. So I just want to briefly talk another thing, that is the existing problem and the future directions in this area. So in those areas, in this research area, the majority of the existing work will mostly focus on spatial feature extraction. They use convolution network or graph convolution network. So the problem is that what if the roadway network is changed or they are expanded? That means how about like we combine the local traffic network with the freeway network, right? So that's very challenging. So you can design some customized graph convolutional neural network or something else. So that's one problem we may be facing, especially in this area. And the other problem is how can we generalize the trained model to other networks? So if we train a model on one traffic network, especially, for example, in the Seattle area, then how can we apply this model into the LA traffic network, right? That's another problem. You may want to try some meta learning or other things, but like in this research area, you can consider how to deal with that problem. And the next problem is when we deal with the spatial feature extraction, then the temporal feature actually has some more challenges, especially some special event happens. And this is actually the VMT, like the vehicle miles of travel during the COVID-19. If we use a pre-trained model to forecast the traffic, then the predicted results may fail because the whole system, the whole traffic system shut down during the COVID-19, and it has apparently different patterns. Then how can we deal with this problem? So in one of our new work, we just try to conduct some online training. So we iteratively update our training set. So that's one, and then we iteratively update our model, right? So in that case, that's how we deal with that. And there's a lot of other ways to deal with this kind of challenges. So you can just think about that. And that's what we want to talk about, like the future directions. For the spatial part and for the temporal part, there's a lot of other challenges. You can consider how to deal with that and conduct your own research. And I think that's pretty much about my presentation today. If you have any questions, just feel free to ask. Thanks for your attention. Yeah.
Yes, thank you, Jiang. That was a really interesting presentation. So at this time, we will do a Q&A session until the turn of the hour, and the webinar will be over. So I want to get things started with a question, actually.
Yeah, sure.
So when you're creating the graphs for your for the network, this may be a little bit of a silly question, but do you differentiate those graphs based upon like direction of travel? So would you have like 2 different nodes, I guess you could say, for each direction? Because it seems to me that you know, especially on divided highways, to predict the future travel of nodes, you know, you'd want to use downstream nodes, right? because that'll show the sort of the traffic that's going to come to the node. So do you differentiate those nodes in the graph, or is that sort of incorporated in a different way?
Yeah, right. Actually, we differentiated those roadway links, or the nodes. So as you mentioned, the freeway, they are bidirectional and they have apparently different travel patterns. So we just try to use different like nodes to demonstrating the two direction of the freeway link. And actually, although those maybe two links, like they are very close, they are parallel with each other, right? They are actually very far away in the graph because they are not connected in the freeway link. Normally that's the case, yeah. Okay, yeah, like, do we have any other questions? You can just feel free to speak out.
And you can also write them down in the chat if you don't want to unmute or something like that, and then I can read them to Jiang as well.
Yeah.
So we'll give people, if people are typing, we'll give them a minute to type in their questions.
Okay, great.
All right, while people are typing, I'll do some finalizing announcements, if you will. The first is that, as I mentioned in the beginning of the webinar, this is being recorded. So once this is over and we get the recording downloaded and such, this will be placed on the PacTrans Doctoral Webinar website. So if you want to go back, watch any of this content, or if you have, friends or anyone else who you think would find this interesting, you can point them there. There's also an archive of all the other webinars we have done so far on the website as well. So if you want to learn about some of the other topics that have been covered in previous webinars, all those recordings are also included. So I would highly recommend you to check out that resource to kind of see some of the other projects that are happening in the transportation field. Furthermore, I would like to quickly announce that we will be having another webinar in approximately a month's time. We do not have the exact date set up for that yet, but so I just want to give you all a heads up to be looking for in the next week or so another message indicating a future webinar that will be presented by John Ash in the beginning of November. So look for that as well. And I guess at this point, there aren't any questions. So here comes one. Perfect.
Oh.
Never mind. So the question reads, you talked about using reverse I assume that's supposed to be LSTM, to consider the upstream and downstream traffic. How is an LSTM model can consider spatial correlations in upstream and downstream traffic? Isn't it the task of a convolution operator to do that?
Oh yeah, yeah, that's a very good question. So basically, when we see LSTM, actually, you can consider the here. So we consider like the input data is a vector, right? And when we use those LSTM, actually, the inputted vector will be handled by this cell, and the correlation or the relationship between different nodes, that's we can refer to like the upstream and downstream. The relationship between those different nodes will internally like possessed or captured by this LSTM. But because those kind of network are kind of black box, we cannot interpret them, because as you can see, that's this is the LSTM functions, and the computation is highly like highly non-linear, and we cannot easily capture their relationship by using a very specific parameter or using some weights. So that's why we mentioned that those LSTM based model, they are lack of interpretability. And as you mentioned, the spatial like correlation can actually be captured by the convolutional neural network. Yeah, that's true. And that's why there's some other methods, there's some other work. They also use the convolutional neural network plus the recurrent neural network to fulfill the traffic prediction task as a whole. And yeah, so that's basically the reason, or see the difference. Yeah. Yes, thanks for the question.
Another question in the chat. I guess it says that you've published your code on GitHub. Are you publishing the new code for the new version of your model as well?
I think so, but like for the TGC-LSTM, because that work was done 3, even 4 years, and we have 2 versions. If you find the code has some problem, you can feel free to let me know. Yeah, I can try to answer the questions. Yeah, you can just send me an email or you can contact me with some other methods. That's both okay. Yeah.
Great.
Okay, great.
It looks like we are just about at 11 o'clock. So unless there are any final questions anyone has, I think we can end it here. Thank you all very much for stopping by. This has been a very excellent event. And also a big thank you to Zhiyong for presenting. I'm sure we would all applaud if we were in person, but yes, thank you all for coming. And as I mentioned before, if you're interested, look for the recording on the PacTrans Doctoral Webinar website. Thank you all very much.
Yeah, thank you.